So, are you able to hear me now?
Yeah, yeah,
Okay.
it's
So,
audible.
are you teaching somewhere?
No, I'm working in an industry.
Oh, awesome. And what about you, Yashas? Am I pronouncing
No,
your name
ma'am. Yes,
correctly?
yes, ma'am. Yes.
Okay. So, you are also teaching somewhere?
No, ma'am. I'm a student.
Oh, which college?
Ma'am, big college,
Oh,
Delhi.
oh, awesome. So, you're from North itself.
I'm a scholar, research scholar.
Oh, so you're
Yeah.
also studying somewhere?
Research we are doing as part of the coursework. We have to select one core subject, so I choose this one.
I see. Interesting.
Yeah.
Okay. So, okay, we will start with where we left. So, now I wanted to talk about some of the PCA examples. One such example is face recognition. These slides are being taken from this link, and I have shared the link to the slides itself. So, now this face recognition is that the challenge is given the faces, we want to identify the person, okay, based on certain images, and these identifications should be robust to the glasses, the lighting situations, the brightness, the contrast of the images, and so on. Now, these images are very small scale resolution images. They're just 256 cross 256 images, so not very high dimensional images. But still, if you look at it, you'll see that this is still 2 to the power 16 pixels per image, right? And that's a lot. So each image is now being represented by 2 to the power 16 pixels, a very high dimensional data. And if your pixels is not even binary, then it becomes further larger lot of information to store. So how can we reduce such a high dimensional image to some low dimensional manifold, like the mapping from high dimensional to low dimensional, and then that low dimensional space should be good enough to reconstruct it. Okay. Is the recording being done? I hope so it's being done. Okay. So how to do that? So suppose we are given an images. The first initial, the simple method is that we will build a PCA. We will apply PCA on the whole data set of the faces, and then we will classify based on the weights. So how we do this is may not be useful, but right now what I want to say here is that how can we compress these high dimensional images to some low dimensional space where that classification becomes easy for us. Okay. So for this, we have to find the principal components, and that's how we try to find the principal component, and this is how it looks in this low dimensional space. So once you compress these images to really low dimensional spaces, this is how it will look. So most of the information regarding the brightness, the contrast has gone, but it is still sufficiently able to capture the facial features. For example, you can see the mustache here, the nose here, the glasses here, or maybe the shape, the outlines of the hairstyle, the way these cheekbones are rising, and so on, right? So this is some low dimensional latent space. And now this low dimensional latent space should be good enough to reconstruct the images as well. So if you look at the reconstructing images, you'll see that this has somewhat constructed the images to a very similar faces, right? These are still identified as human faces, okay? So this latent space to which we map the data is good enough. Also, some of the heuristic, some of the results which were being found is that this is faster to train if the variation in the training data is less. Like, for example, there are no classes, right? Or the if it is in the same lighting conditions, then what will happen that when you are downsampling the data, not downsampling, when you are compressing the data, uh, since the variation is less, or you are minimizing the variation across certain dimensions, it will be still able to reconstruct the images very close to the initial images, right? So then it will work much better. Similarly, I want to show the other examples. One is for image compression. So suppose this is an original image given to you. It's a 372 cross 492 images, and each patch is an instance which contains 12 by 12 pixels on a grid. Okay, and this is how this image looks like. And the idea is how to compress this image to some low dimensional space from which we can reconstruct the image, which looks very close to this original image. So this is the PCA dimensionality here. So there are 150 PCA dimensions they have plotted along with their reconstruction errors. That is the L2 error. So what is the relative reconstruction error? So if you drop the first dimension itself, then the reconstruction error is high. As you keep on increasing the principal component dimensions with lower variances, the relative reconstruction error is not increasing much, right? So this shows that yes, we can drop a lot of these principal component dimensions and can just focus on the dimensions with really high variance. So here's this one PCA compression algorithm output, where you can see that it has reduced the image from 144 dimensions to 60 dimensions. Okay, and similarly, if you further try to reduce it, you can see that this image was definitely more informative than further reduced image, but this reduced image is also able to capture most of the information which was present in the initial image, like there is a butterfly, there are flowers. What we are missing is definitely the detailed information about these flowers. For example, you can not distinguish between these two petals here, but which is clearly can be seen separated here. So yes, we are losing information, but that information is not critical until and unless we are just looking at the bigger picture here, that what this picture is trying to signify to us. So this is how this PCA works. Now I want to talk about its implementation of the PCA and the autoencoder both. So for these things, I'm using PyTorch. So I hope both of you are comfortable with PyTorch. So do you
Yes,
have
ma'am.
some prior experience with PyTorch? Hello, are you still there?
Yeah, yeah. No, no, ma.
So you have never used PyTorch?
No.
Okay. And have you used this scikit-learn library as well? Uh, so have you used this scikit-learn library also before?
No, no, ma'am. Actually, not into the practical session of this.
Okay, okay. No, I think we talked about it some at some point in my past sessions, but have you used it uh, on your own as well? Like, I think it's not the case. Okay, so this is one such library, which is machine learning in Python. It's a library written for machine learning in Python. Most of the machine learning algorithms, whether classification, regression, clustering, decision trees, model selection, pre-processing, dimensionality reduction, and many other such modules are already written for you. So you can directly call these modules from this library and just try to work on it. So let's say we want to implement today this PCA. Okay, so we'll go to PCA and see how to implement that. Okay, so first the uh, so let me just copy this simple example for you, and then we will do it for a more complicated data set. Okay. So, are you familiar with NumPy? Let's make this an interactive session. Wherever you find face any difficulty, or you are not comfortable with any term, or you don't know about it, then please feel free to ask, and I'll be happy to clear it for you. So, have you used this NumPy library before? Are you familiar with NumPy?
Yes, ma'am.
Okay, and you
I heard it, ma'am. I heard it in Python.
Oh, okay, okay. So NumPy is a library which is written in Python, definitely, and it is for numerical computation. So it basically for when you have computations to be performed on arrays, then we generally go for NumPy because it has written all these functions with arrays and will help you in faster processing of it. Okay. So now using these two libraries, NumPy and sklearn, we will try to implement PC in a very simple data set. So here we have X, which is just a simple array, And how many inputs are there? 1, 2, 3, 4, 5, 6. So there are 6 inputs. Each input is two-dimensional. So you remember that X matrix we created, which was n cross t in the lecture slides here, right? Remember this X for PCA? So this X is nothing but n cross t matrix. So here, in this example, this X is representing that matrix where n is 6 and d is 2. And we want to do PCA on this data set X. So we are calling the PCA function from this library sklearn, and we are passing the number of principal components we want to have. So we are just passing that we are interested only in 2 components. And now we are fitting this PCA on this data set X. Okay, and we want to now print here these the explained variance ratio and the singular values. But before that, let me first walk through you what PCA algorithm module is written here. So PCA is a module which you can call from this library sklearn.decomposition. It takes these as the following arguments. The first is the number of principal components you are interested in. So if I want to reduce the dimensionality of some, let's say, 1000 dimensional data to 10 dimensional data, then I'll be putting a number of components as 10 here. Okay, and this is the most important argument to be passed. Once you have done this, what it returns is basically it returns, so it has certain attributes, and using these attributes you can see. So just a moment. Yeah. So here attributes is the components. So these are the principal axis and feature space which will be representing the direction of the maximum variance in the data, and which will be the anti-area of shape. So it will be number of components, common number of features, and that's how it will be written. The other attribute will be explained variance, which will be an again a NumPy array of shape, number of components, and it will be returning the amount of variance explained by each of the selected components. The variance estimation uses number of samples minus 1 degree of freedom, but for now you can ignore this detail. What you need to remember is that this explained variance attribute is basically capturing the variance explained by each of the principal components that has been selected. Then explained variance ratio is percentage of variance which is explained by each of the selected components. Okay, so this is similar as in shape as the explained variance here, and then singular values corresponding to each of the selected components, and then the mean and the number of components which you have sorry, just yes. So now I think these features, these attributes you can ignore for now. The most important one is basically the explained variance of each selected component and the ratio of it. Okay, so now we will try to see how it works for our case. So if you see, we selected 2 components, right? And once we selected these 2 components, number of components, we got the variance ratio of each component as this, right? And these are the singular values. So you can see that the first dimension has the highest singular value, followed by the second dimension which will have a less singular value. Now if I put it 10, so you'll see it will, okay, it cannot reduce. So the number of components are not supposed to be greater than the dimensionality of this data. So here we have 2-dimensional data, so we can have a maximum of 2 components. We can also reduce it to 1 component, and in that case it is giving you only the first principal component, which is explaining 99 times of it, almost 99% of the variance ratio is there. Okay, and if you want to see how the reduced data looks like, we can also do that. So for this, what we will do is we will call this function PCA.transformX, and now you will have the reduced data set. So with this, we will have now X reduced is equal to PCA.transform X. And let me print both initial data and reduced data. Okay, So this was our initial data, and now the reduced data is this. So data from a two-dimensional data we have reduced it to one-dimensional data, and each instance which was initially two-dimensional, like for example this first input -1 is now being represented as a scalar value of 1.38. Okay, now to visualize it also we want to see how it looks like. So for that what we can do is, or maybe I can do one thing for you. We can even visualize this. Just give me one moment. So we are still doing it. So basically we now want to see how these two data looks like. So I can simply plot the initial x, plt.scatter x, and plt.scatter x reduced. So now we will see how these initial data and reduced data looks like. So you see, maybe I can mention the color also. Dot legend. So in case you are not familiar with, matplotlib.pyplot is another library which is being written for visualization. So it is similar to what kind of, so have you used MATLAB before? Uh, so most of the functionalities in MATLAB regarding visualization we can do using this library here, matplotlib.pyplot. Then we have plt.legend. Let me write original data and reduced data. So you'll see that this was the original data and this is the reduced data. So if you see, this data is still able to capture similar variance, right? Okay, so what I mean here is that from two-dimensional we went to two-dimensional, that's true. But if you see, we have somehow rotated this data, right? The pattern of the data is still the same. It goes like something like this. It is still something like this, but the PC has just rotated it into another direction where the variance can be explained maximum. Okay, this will be more clear if we do it for another example. So let's say we use numpy.random and we use Gaussian here. So we tried to have data from a Gaussian distribution, and let's assume it to be a high dimensional data. Okay, so here x is equal to so this is coming from a Gaussian, and it's basically we are sampling 100 inputs, each of 10 dimensions, and now we want to apply PCA to it. Okay, so yes, so the same thing which we did here, we are going to do it here. And now we cannot plot this initial x because it has 10 dimensions, so we will not plot this. We will just plot x reduced, y reduced. Okay, and see how it looks. So this is how it looks. Now if you want to see does it look like a Gaussian distribution or not, so you can try to find the mean. So let me do it even for 1000 and maybe then it will become clear. So you'll see that even it was initially a 10-dimensional Gaussian distribution, but now it has been reduced to a 2-dimensional Gaussian distribution. So you can still see that this is more concentrated towards the center, which is 0, which is supposed to be the, because we have sampled these points from a standard question, which means it has a 0 mean and unit variance. So sampling the points from that 0 question, 0 centered question, and then the mean, the variance was 1 there, right? It was a 10 dimensional data. Now the similar thing you can see it has been captured here as well, right? So this is how the PCA is working. So PCA is trying to find the directions along which the variance is maximum, and beyond certain threshold, or depending on the number of principal components you are interested in, you can leave out the less important principal components there. Is this clear so far? Any questions on this? Anything regarding the implementation part, or any module or attribute of the functions we have used from sklearn image, or the visualization, or anything regarding why this visualization looks like this, or any such questions? Things are clear so far, right? So shall we move to autoencoder then?
Yes, ma'am.
Okay. Now let's do the same thing for the autoencoder part. So how to do that? Instead of writing the entire code, let me use the PyTorch itself and it will show you. So okay, you also mentioned that you're not familiar with PyTorch, right? So maybe we can then start doing it from the scratch, and it will be a good way of learning it. So PyTorch is a library, it's a deep learning library, and where you can encode all these deep neural networks. You can,
How to? It's open source. It's not open source, ma'am.
yes, all these libraries are open source. You can
Okay.
just go to their
Ma'am, can
website and
you just
install.
share me the link so that no, I will just download it and try to install.
Okay, so for downloading purpose, you need to go to this start get started thing, and depending on the configuration of your system, you can just run this command in your terminal and it will be installed. Okay, so you need to
Okay.
fix which, what is your OS, is it Linux, Mac, or Windows? Similarly, the package you're talking about, whether you're installing it using a conda or you are installing directly using the pip environment, the language you want to work on. So I think you'll be going for Python. It's the easier one, and the platform. So it needs CUDA. So you need a GPU for this. And in case you do not have a GPU, then you can just opt for CPU. But the actual performance boost comes with CUDA. Uh, okay, and then just run this command in your terminal and it will be installed. So once you have installed the PyTorch, so, okay, maybe I can just show you a small tutorial on PyTorch. So this is how you import the torch. Once you have PyTorch installed, you can just import it by writing this statement, import torch, and it will be loaded. So suppose I have a tensor, or I want to create a array. So let me go torch.arange of 100 dot reshape 10 comma
You're
10.
sharing anything?
Oh, are you not able to see the screen?
No.
Oh, okay, okay. I was sharing and never stopped it. So, are you able to see the screen?
Yeah, yeah, yeah.
Okay. So, what I'm saying is to download the PyTorch, you need to open this PyTorch website, go to the Get Started section, and start downloading it by running this command. This command will be decided based on the choices you made, whether you choose a stable version or a nightly version, what kind of Linux OS you are using. Is it a Linux, Mac, or Windows? The package here means in which environment you are going to install, whether it is you are going to install inside a Conda environment or a pip environment, the language, and GPU. So if you are not having any GPU access, then you will go for CPU. Else you can choose the compatible CUDA version and just run this command on your server or on your local machine, and it will be installed. I think this is your first time for PyTorch, so maybe I can give you a brief tour of what PyTorch looks like, and then we can deep into autoencoder. So Torch. So here I have imported this library PyTorch by writing this statement import torch. Now here I am creating a tensor A, which is uh, created using this statement. So let's try to parse it one by one. Torch.arange 100. This will return you an array of size. It will return a one-dimensional array. So it will return a one-dimensional array, and the values in that, sorry, it will return a one-dimensional tensor, and the values in that tensor will be 0, 1, 2, 3 up to 99. So that's what torch.arange does. So if I change this 100 to 1000, it will be 0 to 999. Okay. Now I am reshaping this into a new size of 10 cross 10. So right now, what was the size of the tensor here? So to print the size of the tensor, we just have to call
1
tensor
cross 1000.
1 cross. No, it's not.
1000.
Yeah, it's only 1000. It's a one-dimensional data. When you do 1 cross 1000, it becomes a two-dimensional data, right? Where the dimension of the zeroth axis is 1. Got
Yes.
it? But this returns a 1D data. So it's simple 1000. And now I'll try to reshape it to a new data. So what will be the size of the reshaped data?
10 cross 10.
Yes. So it will be 10 cross 10 and it will look like this. So we can even print it. So have you used PyTorch before, Yashas?
Yes, ma'am.
Okay, awesome. So maybe then we can just take a very quick tour of PyTorch and we'll then move to autoencode. Okay, so let me take you to the torch and we will just look at some of the important functions here and a small tour thing. Okay, one important one other can be that we have this array A, right? Now suppose I want to sort this array and I want, so how can I sort this tensor? What will be the way of sorting this tensor? What should be the command? Yashas, would you like to say something? Hello?
Ma'am, can you repeat the question?
How to sort this array, tensor?
What function should be there?
I'm unable to hear you. Please, can you speak bit louder?
There should be a dot sort function.
Yes, torch dot.
Sort
Yeah. And if I want to sort it in a descending order?
uh, rev sort or something like rev should be there. Reverse equal to true.
No. So in PyTorch, it's very easy. You can just say descending is true. Okay, and now it will sort the array in descending order, a tensor in the descending order. So let me print this new array, a new tensor. So you can see here, right? It has been sorted in descending order. Another question. What does A is here? Is it a tensor, a tuple of tensors?
Answer.
No, it's a tuple of tensors. So it's basically A sorted, comma, sorted indices. So what it means is So one is sorted and one other is sorted indices. So now this has been sorted, right? 987654321 So this is your tensor which has been now sorted. The other is the indices. What does this indices mean is this number 9 was initially present at which index? It was present at the last index. So you have 9. The second number which is there in the sorted array was presented at which index? 8 and so on. So the indices is the indices of the elements in the initial unsorted array which when arranged according to this will result in a sorted array. Is that clear?
Yes.
Okay. Another question. Along which axis has been the array sorted? So which dimension across which dimension it has been sorted?
Along the horizontal line.
Yes. So which dimension should we call it, 0 or 1?
One.
Yeah. So it has been sorted across 1. What if I sort it across 0? How should it look like? What should be the output now? If I sort this array in uh, across dimension equal to 0.
The output should be the same then. There should not be any change.
Are you sure?
No, no.
Okay, let's see. I think the output changed. Can you explain why?
Ma'am, because we have sorted it in descending.
Yes, we are sorting it in descending. That's why even when time equal to 1, we said it was changed, right? The reason why it has changed is because now it is sorting across each column. Initially, it was sorting across the rows, right?
Yes, sir.
With dimension equal to 0, now the columns are being sorted. And since we have made descending equal to true, they have been sorted in descending order. And so the indices have also been changed. Maybe this is not clear because this array was already in some order, but let me give you an arbitrary array here. And let's see how it works. So suppose my new array here is, instead of this, let me have a is equal to torch.tensor. So now you can see that the shape of the array is 2 comma 5. This was the initial tensor 147235371. Now this tensor has been sorted in descending order across dimension 0. So when you see it, all these columns are being sorted in descending order. So the first column is 5 1, the second column is 4 3, 7 7 2 2 3 1. Now let's look at the indices. It says that the initial array, the first element in the first across. So now across the 0th dimension, the element present at the first index should come before. So we'll have 5, which is there. Then comes the 0th index element, which is 1, which comes here. Similarly, 0 1. So the second column was already sorted in descending order, so no change has been done. And then indices remain in their initial order. Elements remain in their initial order. Similarly for the third column, so for the fourth column, and so for the fifth column. Except for the first column, all the elements are in their initial order. Is this clear? That's what this indices is going to tell you. Okay. Now let's try to look at some other code of thresholding it. So suppose I have a tensor here. So what will be A now? Why is there 1 here?
These all are the elements greater than 10.
Yes.
So
So when I am doing this A of A greater than 10 equal to 1, it means that in this tensor, all those elements which have a value greater than 10 should now be assigned a value of 1. So that's why you see this. A of A greater than 10 becomes 1. So all of them become 1. Similarly, we can have multiple operations and we can then change it. Then there is something called masking. So let me create a mask here. B is equal to uh, torch dot zeros of shape A dot shape, and P equal to um, let me let's create some of the elements in this tensor to be 1. So P of 0 comma 2 is 1, P of 1 comma 3 is 1, and 1 is 1, and P of 4 comma 0 is 1. So this is how the mask looks, and now I try to mask it. So I say that A is equal to A dot B. So what will be the output? Only those elements of the A tensor will now be retained which have 1 in the corresponding locations in the mask, right? So when we multiply the tensor A with the mask B, only those elements are being retained which have corresponding 1 in the mask B, and all other are being 0. So this mask is useful in deep learning at most of the times when you have to mask certain inputs, or when you have to mask or maybe when you have to apply the attention to the inputs, then you need such operations there. Okay, and let's look at what else we want to do. Yeah, another good thing will be concatenate. So suppose there are two tensors. A is equal to torch dot stack, sorry, torch dot a range of 10. P is equal to torch dot a range of 10. Okay, and now I want to create an array by concatenating it. Stack a comma b comma time equal to 0. So what will be the shape of C?
one-dimensional tensor.
Yes, so A and B will have the shape 10 10, and what will be the shape of C? Because we have stacked these two tensors across the dimension 0, so it will now be the shape of this C will be 2
Dimensional
comma
tensor.
10, where each row will be this one of the tensors. Okay, if I change it to 1, then what will be the shape?
I'm your screen.
Hello?
Slide is not visible now.
Oh,
Your
okay.
screen.
Is it visible now? Is it visible now?
Yeah, yeah,
Yeah.
yes.
Okay. So what I'm saying is that we have two tensors. One is this A and B, and now we are stacking them across some dimensions. So when we stack them across dimension 0, The shape was 2 comma 10. What will be the shape when I stack it across dimension equal to 1?
It will be a one-dimensional tensor only.
Are you sure?
Yes, sir. It will be added in the row.
No, it will be 10 comma 2. So when I'm doing this stack and I'm giving a dimension, it creates a new dimension. And whatever the dimension I'm asking, it creates a dimension across that dimension. So when I say dimension equal to 0, it stacks the tensors as the row of this new tensor. When I added dimension equal to 1, it stacks these tensors as a column of this new tensor. Okay? The other alternative can be some torch dot v stack. Sorry, h stack. So it will now try to horizontally stack these two tensors a comma b. And let me print the shape of d as well. So what is happening here is when you're doing the h stack or v stack, that is not adding any extra dimensions there. Because the horizontally, so it's a tensor, right? It's a tensor of one dimension and they are being stacked. And similarly, if you do with v stack, it will be done because now the two tensors are being placed one above the other. So it will add an axis. However, when you're using a stack, it will always add a dimension. So that's the difference there. Is this clear? So basically, when we try to stack something, it adds a dimension, new dimension, and that dimension along which the new dimension will be added is defined by this parameter div. Okay. Other than that, so you have done stack, reshape. Yeah, one other thing could be squeeze and unsqueeze. So A is again, let's create something like this. And I say A is equal to A dot unsqueeze. Can you now tell me the shape of A? So unsqueeze adds a dimension and the dimension is added across this, the value which we pass. So what should be the shape now? 1 comma 10 is, so basically I said that the 0th dimension is the one where I want to add another dimension, right? So the 0th dimension will now become 1, and what was the initial dimension of A? That will become 10. If I would have changed it to 1, it would have become 10 comma 1. And let's do it again. Now if I add it again at 1, it will be 10 comma 1 comma 1. Or if I do it across 0, it will be 0 comma 10 comma 1. Sorry, I mean 1 comma 10 comma 1, because across the dimension 0 it will add 1. Okay, so this is one another important or very frequently used operations, squeeze unsqueeze. Then there are certain mathematical operations which we can perform easily on tensors, like absolute function. For that we can have simply ABS. Then the other one which is very common is using this a sine h, a tan, which are generally used in the loss function. So you can directly call it. Then clamp is the one which clamps all the inputs to some image. So if I write clamp A, is clamp A or A dot clamp? I think it will be A dot clamp, right? It's an operation on a tensor. So if I say A dot clamp, min equal to 5, max equal to 10, A equal to A, print A. So what will happen is that now the minimum value will be 5. So any number which is less than 5 will be 5, and any number which is greater than 10 will become 10. because we started with an a range of 10, so there is no number greater than 10, so nothing has changed. But all those numbers which are lesser than this minimum value has been clamped to the past minimum value, which is 5. So this is clamp.
Can you please repeat what clamp does?
Yes. So what clamp does is, suppose you have a tensor and it has lot of values, and let's say the minimum of the tensor is 10. Okay. The minimum value in the tensor is 10, and you passed in clamp minimum as 20. It means all the values less than 20 will be termed as 20. So now it is forcing the minimum of the tensor to be 20 and not 10. And this will happen only if all the minimum values are being replaced by the new minimum value, which is 20 and 5 in this case. So let me print A
So
also.
what does the max argument do?
Max does similarly for the maximum. So maybe I can change it. So let's say the minimum here is 3 and the maximum here is 7. Now in this array, initially, sorry, yeah. So initially this array has all these inputs, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. After clamping, all the numbers which are less than 3 are being changed to 3, right? 3, 3, 3, 3. And all the numbers greater than 7 are being changed to 7. So 7, 7, 7, 7. You see the change now? So
Yes,
this
I'm
clamp
got
function
it.
is now changing the minimum and maximum of your tensor. Another good option is argmax and argmin. So I can also do this. Print a dot argmax. Dimension is, so what squeeze will do is, all those dimensions where the value is 1, they will be squeezed, they will be removed, and only dimensions with value greater than 1 will be retained. So what is the dimension of this a? It's 1 comma 10 comma 1, right? But when I'll do a squeeze, it will just become a single dimensional tensor with value 10. So let's print that as well. Print a dot shape. So first of all, a dot shape. So now what has happened here is that when we did a squeeze, the dimensionality has reduced from 1 comma 10 comma 1 to just 10. We did the argmax. Argmax means what is the maximum element in this tensor. The maximum element is 9. What is its indices? It's 10. So that's what it is written. Torch dot argmax of A is this. That is the 10th element is the maximum element. Sorry, the 9th element and the 9th index is the maximum element. So it is returning the index 9. And this is the output with the clamp thing. Okay. Similarly, you can have argmin, which will return the indices of the minimum element. Okay, I think these are the very most overused operations. But other than that, you can go through this document. It's a long document, and you can just try to first find if there is something like that, and then you can do it. One another I would like to say is torch dot random, which is again a very used operation. So torch dot random of shape 10 comma 4. will return you a random tensor. So this is done to sample some random numbers in an initial array. Generally, we do this random either for the weight initialization of the neural network, again for which we have other methods like Xavier normalization, K-mean normalization. But still, we sometimes want to have some kind of randomness in the algorithm, and then we have to sample certain numbers from this random function using this random function. So if you're familiar with NumPy, you will find Torch to be very similar to NumPy. It has almost similar functions uh, as you can find in NumPy. The only difference is they are for tensor. Okay. With this, I'll also like to point out how you can convert a NumPy array to a Torch tensor, and how can you convert a Torch tensor to a NumPy array. So suppose A is my NumPy array here, np dot random dot random size 10 comma 4 print. So A is a NumPy array, and now we want to convert it to a tensor. So that's very easy. Just call this function torch dot from NumPy of A, and now A will be a tensor. So you can see the difference. Initially A was simply an array, and now A is a tensor, and the type of the tensor is float 64. Similarly, we can also convert the tensor to NumPy, and for that we will do A is equal to A dot NumPy and just print A. So it is again a NumPy tensor, a NumPy array. So from array to tensor to array. Again, all these tensors right now on CPU. If you want to convert it to CUDA or GPU, we have to do A is equal to A dot CUDA, and now this will be a CUDA tensor. So okay, the CUDA is not available right now because I'm using Colab, but ignore it for now. So, but you can always convert it to GPU tensor by calling the function CUDA. Note that CUDA tensors cannot be converted to NumPy directly, so they first have to be converted to a CPU. They have to be moved from GPU to CPU, and then only they will be converted to a NumPy array. Okay, right. I think most of these operations we have looked at it, and then you can go through this uh, documentation, and maybe in the next class or next time whenever we meet, I guess it is going to be again Tuesday, you can ask the functions which are not clear to you, and we can even do a demo just like this. So this is the I have pasted the link to the PyTorch documentation where you can find all these functionalities which are being given in the torch for the tensors, and if possible try to play around it and see how it works, and then maybe in the next time we meet we can discuss some of the issues which you are facing while uh, working with them. Okay, the other thing with Python, the next is the torch vision, which is a very important module for working with vision datasets. So this torch vision package consists of all these popular datasets like MNIST, CIFAR 10, CIFAR 100, SVHN, Fashion MNIST, and so on. Different model architectures like ResNet, AlexNet, MobileNet, and so on, Inception. And then some of the image transformations which we need for training the model, like random crop, rotation, flipping, contrast adjustment, brightness, and so on. So whenever we have to work with vision datasets, we will be using this Torch Vision package. Similarly, to work with audio, you will be using Torch Audio. For text, Torch Text, and so on. Now, I want to use, so I think if you have attended, if you were there in the previous sessions, you must have seen uh, this torch vision use where we used it to get to create a neural network, MNIST neural network, train on the MNIST dataset, and we worked with it. So maybe I can just walk you through that for now. Okay, not this one. Um, so I'm just doing a brief retour of this thing because this will give you an idea about how these torch vision datasets work. Perfect. So I am calling the torch vision dataset here. So we have imported torch. From the torch vision package, we are using these transforms. And from torch vision.datasets, we are using MNIST. We will be experimenting on MNIST. It is a small dataset which comprises of handwritten images similar to this. These are grayscale images, and um, it's a 28 cross 28 image where each pixel is either 0 or 1, and they just show these handwritten images. Okay, so this is the dataset MNIST from and how. So first of all, what are the random transformations? So the random transformations are, maybe I can show you one more slide. No problem, we can write a simple code here. So um, okay. So there are certain transformations which are available in this torch vision transforms. One is that random erasing. So what random erasing is does, it randomly erases some part of the image. Okay. In case of random resize crop, we will randomly crop an image and resize it to the size which is being passed as an argument here. Random rotation will rotate the image by certain degrees. Gaussian blur will try to blur the image to reduce some of the details. Okay. How to apply transform? So for applying transform, what we are doing is, first I want to show you how these transforms look like. So this is your images. Now this is actually a collection of how many images? 1, 2, 3, 4, 5, 6, 7, 8. So these are 16 images. Each digit is one image. Okay, I have shown here it as a collection of 16 images for better visualization, but each of this is a image. So there are 16 images here, and the first is random erasing. So if you see that for each image a small part of the image has been erased. In the 7, a small erasing has been done here at the end. In case of 2, it's here. In 1, it's in the top part of the image. For 4, it's here, and it's a random erasing, so not all the images have been erased, some of the images has been erased. And also, if some erasing has been done in the background, it will not be visible to you. Okay, and so on. So if you want, then there is random resized crop. This is the random resized crop. What it means is it crops the image and it resizes it to the original image. So you can see that this was the image, but now this looks to you a bit larger in size. What has happened is it cropped the center region and then it enlarged it to match the original size. So that's why you'll see that it got bit blurry. It is not as sharp as the original image. Similar for 2, it has been first cropped and then resized to the original size. Similar for 1, then 0, then 4, then 1, then 4, then 9, and so on. The third rotation transformation which you can see is random rotation. Now here all these images have been randomly rotated. So the 7 is now looks like this after being rotated. 2 looks like this after being rotated. 1 something like this. 0 like this, and so on. And the another transformation here is Gaussian blur. So it will blur the images. So now you can see that though this 9 was very sharp, it looks like a blurred 9 here. So these are kind of the transformations which can be applied to images, and they can be multiple such transformations. So I just showed four of them, but there can be many transformations, and you can find them here in Torch Vision package. Just go to the transforms, and then you can see that there are so many transforms which can be applied to an image. Now for example, I did not apply the horizontal flip here, right? Because what will happen if I flip the image after horizontal flip 3 will no more be a 3. So we have to make sure that whatever the transformations we are applying to the images should preserve its label. It should not change the label, or it should not change the meaning of the image itself, right? For example, for 1, horizontal flip is fine because 1, even if flipped, remains the same. But it may not be the case with 4 or 5 or 6. However, for 8, it is still valid. So these transformations, when are being applied to the images, should be ensured that they do not change the meaning of the images. Okay. I'm also pasting the link to this page in the chat section. Try to go through it, and if you came across any transformation which is not clear to you, we can do it again in the next session. Okay. uh, so is there any questions so far regarding transformations and the torch tensors? So Penelope, is it clear to you now, like some basic familiarity with PyTorch now?
Yeah, yeah, yeah. Yes, ma'am.
Yeah,
Thanks.
so please try to do it, just try to practice it. Even if you do not have a setup, just open a collab and try to do some small functions there using PyTorch. Just simple expressions. Maybe like you can try to compute the addition of two tensors, like how will it work, how the multiplication of the tensors will be done, how you can mask it, how can you sort it. So just simple basic tensor operations, just try to do it in a collab. And if you come across any such issues or you are not able to do certain tasks, then just please feel free to ask it in the next time and we will discuss it. Okay.
So
And
this is only used for image processing.
oh, no, it can be used for anything: image, audio, text, any data, any type of data, medical images. Um, right.
So whether any maybe some classification we can do it with this.
Yes. So when I talk about image classification, right, the dataset is still an images, but the task is a classification where each image has to be categorized into one of its label, the classes, right? So
Okay.
this dataset which I have showed you.
Okay. So computational wise, it will be efficient, no?
Yes. It is very efficient and it is very helpful for doing the updating of the model, because now you're not supposed to compute the gradient on your own. The library is doing it for you, right? You just have to call the functions in the right order and have to make sure that whatever the function you are implementing as the loss function should be differentiable.
Okay.
Okay, and this
Okay.
data set which I showed you here, this MNIST data set, this is actually a classification data set. The task is that each of these handwritten images has to be classified into one of the digits. So for example, this first image here has to be labeled as 7, the second image has to be labeled as 2, the third image has to be labeled as 1, and so on. So this is a classification task
So let me
data set.
let me take this example to maybe some communication systems where
Mhm.
suppose some data will be there in different modulation schemes, whether we can apply this and classify this in different modulations.
So how are you encoding your modulations there?
Uh, yeah. Actually, no. My application will be in that direction. So I'm just correlating this one there. Suppose we have some kind of data with the different modulation schemes. We want to classify that in different modulation. Whether we can apply this one there.
Yes, so in that case, your data will not be an images, but it most likely, if you are encoding it as some numbers or some tabular forms or something like that, then that will be the modality of the data. But yes, PyTorch will still be useful if you're using some deep neural networks there, and if you want to do some computation on the GPUs.
So what much is the efficiency of this too?
Oh, this is very efficient, right? So if you do things on GPU versus you do things on CPU, there is a huge time saving, first of all. And it also depends on your application. So how big is your data set? What kind of computations are you doing on the data? What kind of model you are trying to fit in there, right? Is it a simple linear model, or is it a big neural network which needs to be optimized using gradient descent? So a lot of things are there which will decide whether you should use GPU or not. But definitely, GPU helps you in time saving if your operations are matrix oriented and need some kind of backpropagation and stuff, and so on. Like whenever there is matrix multiplication or matrix computations, you should try to use GPU for faster computation.
Okay, thanks, ma'am.
Okay. Any other questions? So do you have any questions, Yashas?
No, ma'am.
Okay, so in case there are no more questions, then maybe because this is already getting late, so even if I start autoencoder right now, I'll not be able to wrap it up. So maybe we can look at the implementation of the autoencoder in the next session on Tuesday itself, because that topic is still going on in the lectures. So that we still have time to cover the implementation part. The theory part is already done. So will that
Yeah,
be okay?
sure, ma'am. Yeah,
Okay, so let's meet next Tuesday at 7, and we'll see the implementation of the autoencoder in the PyTorch.
yeah, sure. Okay,
Okay,
thank you.
okay, bye. Thank you for
Thank
joining.
you.
Bye.